The Superman throws a pool ball.
This is the hockey puck. So what's happening is the hockey puck has some mass, not a lot, and a slap shot comes, wham, hits it. The hockey puck is in contact with the hockey stick for 2 seconds. So there's just a short period of time that there's a force. The force is given, in my case it's so many newtons force. And the question is, what's the position of the puck? So what's its position out here? So if it starts here, I'm going to call this the x-axis, this the positive direction. So what's its position? What's its x final position given the initial position? Well, it's stationary, and it's cruising along here, so it must be accelerating. The question is, what's the acceleration? If I'm going to find that distance, I'm going to need an acceleration, because I know it starts from rest, and I know it ends up moving, and that is going to require an acceleration. So what is it? Well, accelerations are caused by forces. So let's think about the force. So net force causes masses to accelerate. So what are the forces? There's a weight down. There's a normal force of the ice up. But those two are imbalanced because the puck is neither sinking nor rising. But in the horizontal direction, because it's frictionless, there's only one force. That was the force of the hockey stick. And it's given. In my case, it's 0.26 newtons. So that force is going to cause this mass to accelerate. So we can figure out what that is. Just plug it in. F net is equal to ma. So this is the net force, because those two cancel out. If I add up all the forces, those two are gone. Net force is, you know it, you know the mass, so now you know the acceleration. From this you can calculate an acceleration. So now we know that. The next part says, oh no, we still have to figure out how far it's going to go. Well, now that we have an acceleration from dynamics, remember dynamics is the study of forces and the causes of motion. Now that we've studied that the motion was caused by the force and we have acceleration, now we can use kinematics to actually describe the motion. So let's look for a kinematic equation that takes into account time, changes in position, and an acceleration. X final, x initial, plus initial velocity, delta t, plus 1/2 acceleration through time squared. We know time, we know acceleration. Our initial velocity, this is a horizontal problem. We have a horizontal acceleration because of the force of the hockey puck. The initial velocity horizontally started at rest, so that's 0. Your initial position, let's lay down our coordinate system here with this as the origin, so that'll be a 0. And the final is what you want. You can calculate that. Everything else is known. So what's the speed of the puck at the end of that time? That's another kinematic equation. We have acceleration, speed of the puck, the velocity, final velocity, initial velocity, plus acceleration in time. We know the initial velocity is 0. The acceleration will be positive because it's to the right. We know the time, so we're going to be able to come up with a final velocity. It'll be positive, so we'll say that's some kind of speed to the right. The question only asks you for the speed, so just put in a magnitude, which is just a positive value. Okay, so this is a typical example of how dynamics and kinematics are intertwined. We studied the forces, figured out a net force. From the net force, we can come up with an acceleration, and that acceleration structures our kinematics.